There is a relationship between the electric field strength and the electric potential of an electric field, which allows us to determine one of them from the other one. If we know the electric field strength E at every point of the electric field, then we can determine the potential difference delta phi across two arbitrary points in the field. We already saw that the work done by the electrostatic field when it brings the test charge QP from the point P1 to the point P2 can be written in two forms. On the one hand, the work W done between the points P1 and P2 is equal to the test charge QP times the line integral of the electric field strength E with respect to the arc length S along an arbitrary curve between the 2 points. On the other hand, the work W can also be written as the product of the test charge QP and the potential difference phi1 minus phi2 of the electrostatic field across the points P1 and P2. Since the charge QP is arbitrary, the difference between the potential phi1 and phi2 is equal to the line integral of the electric field strength E with respect to the arc length S measured along an arbitrary curve between the points P1 and P2. The other way around, if the potential phi is known at every point of the electrostatic field, we can determine the electric field strength E describing the field. By definition, the force F acting on the test charge QP in the electric field is equal to the product of the charge QP and the electric field strength E. Since the electrostatic field is a conservative force field, the force F is given by the negative gradient of the potential energy U of the test charge QP, where the potential energy is equal to the charge QP times the potential phi. Then we can write that the charge QP times the electric field strength E is equal to the negative gradient of the charge QP times the potential phi. As a result, the electric field strength E of the electrostatic field is given by the negative gradient of the potential phi of the field for an arbitrary charge QP. This equation is formulated in a coordinate-free expression, and we need to choose a coordinate system attached to the frame of reference when we calculate the negative gradient of the potential. Here we can see the description of an arbitrary point P in the most frequently used coordinate systems. In the Cartesian coordinate system, the coordinates of the point P are the projections x, y and z onto the coordinate axes mutually orthogonal to each other. The coordinates of the point in the cylindrical coordinate system are the distance ρ of the point P from the z-axis, the azimuthal angle phi measured between the x-axis and the projection of the point onto the xy plane, and the coordinate z itself. In the spherical coordinate system, the coordinates of the point are the distance r of the point from the origin of the coordinate system, the polar angle theta between the x-axis and the direction of the line connecting the origin and the point P, and the azimuthal angle phi. In the Cartesian coordinate system, the components of the negative gradient of the potential phi are equal to minus the partial derivatives of phi with respect to the coordinates x, y and z. The components of the negative gradient of the potential in cylindrical coordinates are given by minus the partial derivatives of phi with respect to the coordinates ρ, phi and z, where the derivative in the phi component of the gradient is divided by ρ. In the spherical coordinate system, the components of the negative gradient of phi are given by minus the partial derivatives of phi with respect to the coordinates r, theta and phi, where the derivatives in the theta and phi components of the gradient are divided by r, and r times sine theta, respectively. As an application of the gradient formula, we will derive the electric field strength describing the electric field from the potential due to a point charge, which we already studied. We saw that the potential phi due to a point charge q at the point P is given by 1 over 4 pi epsilon naught, times the ratio of the charge q to the distance r of the point P from the point charge. Since the electric potential due to a given point charge at the point P depends only on the distance of the point from the point charge, the potential is spherical symmetric around the point charge. For such a symmetry, the equipotential surfaces are concentric spheres with the centers at the point charge. If we attach the origin of a Cartesian coordinate system to the point charge q, we can write the distance r between the point P and the point charge q as the square root of the sum of the squares of the Cartesian coordinates x, y and z, and compute the gradient of the potential in Cartesian coordinates. The gradient formula tells us that the electric field strength E due to the point charge q is equal to the negative gradient of the potential phi given here. For a constant amount of charge q, we only need to compute the gradient of 1 over the distance r, which is equal minus 1 over r squared times nabla r. Since the Cartesian components of the gradient of the distance function r are given by the partial derivatives of r with respect to the corresponding coordinates, we can compute the x component of the gradient if we substitute the distance r expressed in Cartesian coordinates into its partial derivative with respect to x. By applying the chain rule for the sum of x squared, y squared and z squared to 1 over 2, we obtain 1 over 2, times the sum of x squared, y squared and z squared to minus 1 over 2, times the partial derivative of the sum of x squared, y squared and z squared with respect to x. Here the second factor is simply 1 over r, and the derivative is equal to 2 times x. As a result, the x component of nabla r is equal to x over r. Similarly, the y and z components of the gradient are given by y over r, and z over r. By inserting this result into nabla r, we can see that the gradient equal to the position vector r pointing from the point charge q to the point p divided by its length, which is the unit vector er pointing in the same direction. If we substitute this expression into the original formula, then the electric field strength E due to the point charge q at the point P described by the position vector r can be written as 1 over 4 pi times epsilon naught, times the ratio of the charge q to the distance r, times the position vector r divided by the distance r. We already know this formula, and we represented it with the electric field lines emanating radially from the point charge q for a positive charge, where the topology of the field lines illustrates that the electric field is spherically symmetric. We can exploit such a symmetry of the electric field by choosing a spherical coordinate system with the origin at the point charge q when computing the gradient of the potential. Since the spherically symmetric distribution of the electric potential is independent from the polar and azimuthal angles, the angular components of the gradient vanish and we only need to derive its r component pointing in the direction of er. The derivative of 1 over the distance r with respect to the coordinate r is equal to minus 1 over r squared, which immediately gives the electric field E obtained above, simplifying its computation. We apply the same method to derive the electric field strength from the electric potential due to an electric dipole. We already determined the potential due to a dipole of an electric dipole moment p at the distance r from the midpoint O of the dipole. We found that the electric potential phi far from the dipole is given by 1 over 4 pi times the scalar product of the dipole moment p over the square of the distance r and the position vector r divided by the distance r. Here the position vector points from the midpoint O to the point capital P at the distance r, and the dipole moment p is defined by the product of the charge q and the displacement vector d describing the electric dipole. The blue and red curves running around the point charges minus q and plus q of the dipole represent the equipotential lines of the electric potential. In the vicinity of the point charges they look like those of an individual point charge, but the geometry of the equipotential lines has a drastic change far from any of the point charges. This change indicates that the effect of the point charge minus q does not dominate over the effect of the charge plus q far from the dipole, and vice versa. We can write the scalar product as p times r over r cubed, and substitute the potential into the gradient formula stating that the electric field strength E is equal to the negative gradient of the electric potential. If we apply Leibniz's rule for the gradient of the fraction, we obtain the dot product of the dipole moment p and the position vector r times nabla 1 over r cubed, plus 1 over r cubed times the gradient of the dot product. By applying the chain rule, we can write the gradient of 1 over r cubed as minus 3 times the product of 1 over r to 4 and nabla r. We already determined the gradient of the magnitude of the position vector r, and we found that it is equal to the position vector r divided by its magnitude. As a result, nabla 1 over r cubed is given by minus 3 times the position vector r over its magnitude raised to the power of 5. We can also calculate the gradient of the scalar product of the electric dipole moment p and the position vector r. Since the vector p is constant, the gradient can be written as the contraction of the transpose of the vector p and the tensor nabla r, where the matrix on the right-hand side represents the components of the tensor in a Cartesian coordinate system attached to the midpoint O. In the matrix, a given row represents the gradient of the corresponding component of the position vector, and we see that the elements of the matrix are equal to the Kronecker delta. Since the Kronecker delta represents the components of the unit matrix I, the gradient of the scalar product can be written as P transpose times the unit matrix I. It is also equal to I times P because the unit matrix I is symmetric, and the product gives the electric dipole moment P itself. If we substitute this result into the original equation, the electric field strength E due to a dipole with the electric dipole moment P at the point P described by the position vector r can be written as 1 over 4 pi times epsilon naught, times the difference between 3 times the dot product of P and r times the position vector r over its magnitude to 5, and the electric dipole moment P over the magnitude r to 3. This is the same formula which we already obtained by applying the principle of superposition of the electric field strength in the far field approximation, but it is easier to derive it from the negative gradient of the potential due to an electric dipole. We also show the electric field lines representing the electric field strength due to the dipole, where the field lines are directed from the positive charge to the negative one. If we compare the distribution of the equipotential lines and the field lines, we can see that these lines are always perpendicular to each other. This relationship between the equipotential lines and the electric field lines follows from the gradient formula, as it will be shown. We have already seen that we can illustrate the spatial distribution of electric potential with level surfaces called equipotential surfaces. The electric potential phi of an electric field is constant over such surfaces, that is, the equipotential surfaces consist of those points represented by the position vector or pointing from a given reference point O for which the potential phi as a function of the position vector R is constant. If we choose a Cartesian coordinate system, then the electric potential phi becomes a function of the coordinates, and its level surfaces can be given by the point sets described in terms of the Cartesian coordinates x, y and z. We can also use cylindrical or spherical coordinates if the electric potential exhibits the corresponding symmetry. We normally adopt the convention of drawing the equipotential surfaces with such a density that the potential difference between two neighboring surfaces is always constant. This convention allows us to deduce the magnitude of the electric field strength from the density of the equipotential surfaces, as we already did it from the density of the electric field lines. The density of the surfaces indicates the magnitude of the potential gradient, that is the magnitude of the field strength. In other words, closer equipotential surfaces imply a larger gradient or stronger electric field. Since the electric potential is constant over the level surfaces, its value will not change along the displacement delta S from a point P0 to a point P over the equipotential surface. The smaller the displacement delta S is, the smaller the difference is between the displacement along the surface and the vector pointing from the point P0 to the point P. The directional derivative of the potential phi along the surface is defined in terms of the displacement ds and the vector P0p, as the limit of the potential difference across the points P and P0 over the displacement delta S along the surface, multiplied by the vector P0p while delta S tends to 0. The direction of the derivative is along the tangent S to the level surface, as it is indicated by the vector notation of S in the directional derivative. If the infinitesimal potential difference in the ratio defining the directional derivative is expressed in Cartesian coordinates, then it can be shown that the directional derivative of the potential phi in the direction of the tangent S is equal to the scalar product of the tangent S and the gradient of the electric potential. Here the negative gradient of the potential phi is equal to the electric field strength E, and the directional derivative of the electric potential can be written as minus the scalar product of the tangent S and the electric field strength E. Since the vector S is the tangent to the equipotential surface over which the potential difference vanishes, the directional derivative is equal to 0. Because of the vanishing scalar product, the electric field strength E and the electric field lines must be perpendicular to the equipotential surfaces. We can also demonstrate this relation by applying the work-energy theorem for a charge displaced in the electric field. In the figure we show the level lines, that is the section of the level surfaces of the electric potential phi, where the potential difference across the surfaces is given by the infinitesimal value d phi. Let us suppose that the test charge QP is displaced from a point on the level surface of the potential phi along the infinitesimal displacement ds, and it arrives at the level surface of phi plus d phi. Then the infinitesimal work dW done while the test charge QP is brought along the displacement ds can be written in two forms. On the one hand, the work dW is given by the scalar product of the force F acting against the electric field and the displacement vector ds. By definition, this force is equal to minus the test charge QP times the electric field strength E. The scalar product of the electric field strength E and the displacement vector ds can be written as the magnitude of E times the length of ds, times the cosine of pi minus theta, where the angle theta is measured between the directions of the force F and the displacement ds. If we apply the trigonometric identity for the cosine of the sum of two angles, the work dW can be written as the product of the charge QP, the magnitude of E, the length of ds and cosine theta. On the other hand, the infinitesimal work dW is equal to the product of the test charge QP and the infinitesimal potential difference d phi. The differential of the potential phi can therefore be written as the magnitude of the electric field strength E times cosine theta, times the length of the displacement ds. Here the magnitude of E times cosine theta is equal to minus the projection ES of the electric field strength in the direction of the displacement vector ds. Then the differential of the potential phi is given by minus the projection ES of the electric field strength in the direction of the displacement, times the length of the infinitesimal displacement ds. Since the latter is the differential of the arc length S measured along the displacement, we can formally divide the equation by ds and write the projection ES of the electric field strength as minus the derivative of the potential phi with respect to the arc length S. Here the arc length S is measured along an arbitrary direction as opposed to the equation above it, where S denotes the tangent to an equipotential surface. Although the direction of the infinitesimal displacement is arbitrary, there is a preferred direction for the displacement of the test charge QP in the electric field. If the test charge is brought in that preferred direction, then the projection ES will attain its maximum. Since the cosine of the angle theta between the directions of the displacement and the electric field has a maximum for a vanishing theta, this preferred direction must be the direction of the electric field strength E. As a result, the maximum of the projection must be equal to the magnitude of the electric field strength E, and the maximum of the derivative of the electric potential phi with respect to the displacement S is equal to the gradient of the potential. Then we demonstrated again that the direction of the displacement S, in which the derivative has maximum, is always perpendicular to the equipotential surface, since pi minus theta is equal to the right angle for vanishing theta. The negative sign in the right-hand side of the formula indicates that the electric field strength always points in the direction of the decrease of the electric potential. The formula also shows that the unit of the electric field strength E can also be expressed in volt per meter. Now we will illustrate the distribution of equipotential surfaces in the vicinity of the simplest systems of point charges by plotting the equipotential lines, that is, the two-dimensional sections of level surfaces with discrete color scales. We already saw that the electric field due to a point charge is spherical symmetric around its source. As a result, the electric field lines are radial lines originating from the positive point charge. If the point charge is negative, then the electric field strength points inward. However, in both cases the equipotential surfaces of the potential due to the point charge are concentric spheres with the center at the point charge. The corresponding equipotential lines are concentric circles, and the radial electric field lines are always perpendicular to them. We can see that both the density of the field lines and the density of the circles increase towards the center, indicating the increase in the electric potential and the magnitude of the electric field. This increase is also shown by the distribution of colors around the point charge, where the lighter colors represent the higher values of the potential. We note that the equipotential surfaces forming spheres enclose the source charge of the electric field, which holds for more general systems of point charges as well. The second example also illustrates this fact, where we show the electric field lines and the equipotential surfaces of the electric field due to an electric dipole. The equipotential lines have a reflection symmetry about the plane crossing the midpoint of the dipole, which is perpendicular to the axis of the dipole. However, the potential is anti-symmetric around this plane in the sense that the potential has the same magnitudes but the opposite signs along the corresponding equipotential surfaces in the opposite sides of the symmetry plane. While the different shades ranging from purple through red to white represent the positive values of the electric potential, the color scale ranging from purple through blue to white represents its negative values. The maximum of the magnitude of the electric field strength is still at the point charges of the dipole, as shown by the density of the electric field lines and the equipotential lines. The electric potential is 0 over the symmetry plane, which is also an equipotential surface. The electric field lines originating from the positive point charge and terminating at the -1 are always perpendicular to the equipotential surfaces. Except for the symmetry plane, all the equipotential surfaces are closed and enclose either the positive point charge or the -1. In other words, the two sources of the electric field are always inside some equipotential surfaces. The spatial distribution of the equipotential surfaces around an electric quadrupole is more complicated, but it has similar features. Here we can see two planes of reflection symmetry crossing the midpoint of the quadrupole, which are perpendicular to each other. Both the densities of the equipotential lines and the electric field lines, and the colors between the equipotential lines show that the magnitude of the electric field strength has maxima at the point charges. The colors also indicate that the electric potential in the quadrants with the positive point charges at the center is positive, whereas the potential in the quadrants with the negative point charges at the center is negative. Evidently, the planes of anti-symmetry are equipotential surfaces where the potential vanishes. Except for these planes, all the equipotential surfaces enclose any of the point charge in the quadrupole. We can also see that the electric field lines are perpendicular to the equipotential surfaces at every point. For electric multipoles of higher order, we can establish similar symmetries in the spatial distribution of the electric field based on the symmetric configuration of the point charges forming the systems.